Welcome to this lecture. In this week we have been discussing about integration of measurable functions with respect to a given measure on the domain side. So far we have concentrated our attention on obtaining properties for this integration procedure. In this lecture we are going to look at a very important theorem involving this integration procedure that finally allows us to make comments about linearity of the integration procedure. So let us move ahead with the slides and discuss that result. So this result is called the monotone convergence theorem. So far we have restricted our attention to basic algebraic properties such as multiplication by scalars and certain comparison type inequalities. In the previous lecture we have restricted our attention to a very specific type of integrals over sets, and we had seen that for non-negative measurable functions, by fixing that function and varying the set over which the function is getting integrated, we can get a measure. So that is some kind of a continuity behavior of this integration procedure. We are going to discuss that in more detail in later lectures, but for now we are going to look at certain limiting behaviors for special type of sequences of measurable functions, and that is the content of this monotone convergence theorem. So in this lecture we are going to state it and look at certain applications of this monotone convergence theorem, but the proof will be discussed in the next week, that is week 7. So we are going to assume this and apply this. The proof does not require any linearity property, and we are going to actually prove the linearity property as an application of the monotone convergence theorem. So this is a very important theorem in the context of integration of measurable functions. So what do? We start off with non-decreasing the sequence of measurable functions. So by that I mean, if you take this sequence hn, then hn is less equal to hn plus 1. Great. And you also assume that these hns are bounded below. In particular, you can assume them to be non-negative. So for such a sequence of measurable functions defined on this same measurable space with this given measure mu on the domain side, we are going to consider their integrals. But since this sequence of functions are non-decreasing, so point-wise you can consider the limit function. So this limit function of course will become measurable. So we will comment about that in a minute. But let's look at the integration of this limit function h. Now, since hn is less equals to hn plus 1, we have already mentioned earlier that integrals will also follow the same inequality. That means integrations of hn will be less equal to integration of hn plus 1, right? So therefore, these quantities whatever they are also non-decreasing in n. Okay. So therefore, this has a limit. Now, since hns are going to this limit function h and hns are non-decreasing, each hn is dominated from above by h. So therefore you have integration of hn dominated from above by integration of h dim. What you are saying is that this limit is exactly the integration of h, not the inequality that you get. Alright, so this is an exact equality that the limit of this hns is exactly integration of h. Okay, so several comments before we go into applications. As already mentioned, we are going to prove this in the next week, not now. Okay, so this monotone convergence theorem is very important and it's used multiple times. So for our reference we are going to call it as MCT. So this is for ease of notations. We are going to call it MCT to refer to monotone convergence theorem. Okay. So in the MCT you have this measurable function h because it's a pointwise limit of measurable functions. Okay. So as long as you have the existence of the limit, so here you have the hns to be non-decreasing, so therefore you have the pointwise limits. So therefore h is measurable with respect to the given sigma fields. So measurability is not an issue for the limit function. Great. But it can happen that the limit function h takes values in the extended real line. In particular, it might take values plus infinity, right? It might take that value. the MCT will continue to hold. So even if the hns are real valued, their limits could be plus infinity for some point, so therefore the limit function may take plus infinity. So even then there is no issue, because we have already mentioned that integration of extended real valued functions goes in the similar way. Okay, so again by this approximation by simple functions and all those procedure. Anyway, we need to interpret this integration of h d mu in the case when h is taking values in the extended real line as an integration of extended real valued measurable function. So it's not a problem, so we can define this. Great, but the MCT is applicable even in this case. All right, but important point to note is that given any non-negative and measurable function, by this earlier theorem in week 3, what we had done there is that we had approximated this non-negative and measurable function by simple functions. Okay, so these simple functions approximated a general measurable function which is non-negative from below. Alright, so then these simple functions, we had given explicit construction of that such that these simple functions increase and increase to the given non-negative measurable function. So this falls in exactly in the setup of the MCT, that these hns are certain nice functions, simple of course, in particular they will be measurable, and then hns will be dominated from below by 0, right? So therefore hns are non-negative and they increase to h. So this is falling in the exact setup of MCT. So with this observation, you can now look at this point, that given a non-negative and measurable function h, choose this sequence of non-negative and simple functions hn as mentioned in the previous point Roman 4, continue with that sequence of simple functions. Then as per MCT, integration of h can be computed as the limit of integrations of hn. So if you can compute the integration of simple functions which is appearing on the right hand side, consider the limit of that, then you have the value of integration of h. But remember, we had earlier defined the integration of non-negative measurable functions h as a supremum over certain class of simple functions below h, right? Here we have a alternative definition, alternative expression in terms of a limit, not a supremum. Of course, this hns increase, so therefore this limit is nothing but the supremum over this countable set of values, right? But what is happening is that instead of using supremums as in the general case, general definition, limits are much easier to handle. So this is a very important observation, that by using MCT and using that approximation from below by simple functions, you can compute the integration of non-negative measurable functions by this limit of integrations of the corresponding simple functions. Great. Now this will allow us to do computations in a easier fashion when we want to compute the integration of h. Okay, great. But in this setup of this monotone convergence theorem, we had earlier written that hns, if they are simple functions and increase to h, we had used this symbol. So this was mentioned earlier in that construction of the simple functions, that this simple function increase to h, and that will denote by this upward arrow symbol. But then in the setup of MCT, we can use any general sequence of non-negative measurable functions. Instead of a simple function, you can use a non-negative measurable function, even then the limit holds. So that is the statement of the MCT. And in particular, of course, this applies to the case of simple functions, approximation by simple functions. Therefore, since this is a slightly more general statement in the MCT, where hns are now non-negative and measurable, then we will use the same upper arrow notation to denote that limiting behavior. Okay, that these measurable functions are now approximating the function h from below. Alright. Now, given this structure, that h is a pointwise limit of these functions, so MCT gives sufficient condition for exchanging the order of limit and integration. So given a limit function h of the limit of these functions hn, if you consider these sufficient conditions that hns are non-negative and hns are non-decreasing, under these sufficient conditions, you are allowed to exchange the order of limit and integration. So that's what this is saying, because limit of integrations of hn is nothing but the integration of h. So that is as per the Monotone Convergence Theorem, but observe that H inside is the pointwise limit. So therefore you are just exchanging the order of limit and integration. Okay. So in later lectures we are going to study more results of this type, which will allow us to exchange the order of limit and integration. So this is a very important result which allows us to exchange the order of limit and integration. Alright. Great. With that understanding of the Monotone Convergence Theorem, we are now ready to discuss certain important applications of the Monotone Convergence Theorem. The first one being that linearity property that we have been after for a long time. So take two measurable functions f and g. If you know that integration of f exists, integration of g also exists, then you consider the integration of f plus g. But you would like to connect it with the integration of f plus integration of g. So you have to make sense of integration of f plus integration of g. So if it so happens that infinity minus infinity does not occur, that means that integration of f is equal to infinity and integration of g is equal to minus infinity. If such a equation doesn't occur, or vice versa, meaning integration of f is minus infinity and integration of g is infinity. So if this does not occur, then integration of f plus integration of g is well defined. Great, because infinity minus infinity is not occurring. In such a situation, you can now show that integration of f plus g exists and is equal to this sum of the individual integrations. So this is the result that we have been after for a long time, and this follows from the application of MCT. We are going to discuss this proof of these theorems, this theorem 2, which is this linearity property, and the MCT, which is theorem 1, in week 7. Okay, but we are going to use these facts in the discussions now. Okay, so with this additivity property at hand, we can now say that if f is integrable, then mod f is integrable. So why is this? So if f is integrable, we are given by definition that integration of f plus is finite, integration of f minus is also finite. But then mod f is nothing but f plus plus f minus, and therefore by the additivity property we immediately get that integration of mod f, which is integration of f plus plus f minus, is equal to the separate integrations. But if both of these are given to be finite, then integration of mod f is also finite. But hence what is happening is that mod f is a non-negative measurable function whose integration is finite, therefore mod f is an integrable function. But this corollary, which we have just proved, states that f is integrable implies that mod f is integrable. This is the converse of note 9, where we stated that mod f is integrable implies f is integrable. Therefore, if you combine these results, you have the equivalence of these two statements, that f is integrable if and only if mod f is integrable. And integrability of mod f is nothing but that integration of mod f that is finite. Okay, alright. And just a quick observation once more, that here we are looking at integration of f. The integration of f is now computed as the difference of the integrations of f plus and f minus. If both are given to be finite, in this case the difference is a real number. So that is of observation. When f is integrable, you have these things. Great. But this result for measurable functions, you can now state it for random variables. And you are now just restating these observations for random variables by this, that x is integrable if and only if mod x is integrable if and only if expected value of mod x is finite. Remember, expected value of mod x is nothing but the integration of mod x with respect to the given probability measure. So therefore, x is integrable if and only if integration of mod x is finite, that is expectation of mod x is finite. And in this case, of course, expected value of x is a real number. But then if x is quasi-integrable, you have to be careful. In this case, exactly one of x plus and x minus has a finite integral, other has infinite integral. In this case, expected value of mod x is the addition of these two quantities. One of them is finite, other is infinite. So therefore, expected value of mod x is infinite. So in the case when x is quasi-integrable, expected value of mod x is infinite. But in this case, expected value of x is plus or minus infinity. This thing we are considering now when x is quasi-integrable. Okay. In the basic probability course, we had not considered the quasi-integrability case, but we had considered the existence of these expectations through this condition that expected value of mod x is finite. Okay, but even if expected value of mod x is infinite, if x is quasi-integrable, we can still talk about expected value of x. That is the power of measure theory that we are using here, and since we have defined the expected value of x through these measure theoretic integrations, we are going to consider this in the cases when x is quasi-integrable. Great. Alright. Now, an important fact here is that the additivity of the integral that we have just discussed will allow us to prove this kind of a statement, that under appropriate hypothesis, if you have two random variables x and y, then expected value of x plus y is equal to expected value of x plus expected value of y. Now remember, in your basic probability theory, you had proved similar results using the fact when x and y both are discrete or both are absolutely continuous. Here we are not stating that. Here we are saying if x and y are two random variables, be it continuous, be it discrete, doesn't matter. X could be discrete, y could be continuous. Even then you can talk about their addition and their expectation, and then you can split the expectation by the linearity of the integration and write this. So here the appropriate hypothesis is simply that expected value of x exists, expected value of y exists, and their sum is defined. That means infinity minus infinity situation does not arise on the right hand side. If that is the case, then you can talk about expected value of x plus y being equal to the right hand side. Great. Now, combining all of these results together, you can now say that this linearity of the integration holds. So what we had proved earlier is that scalar multiplication was allowed. Now we are saying additivity is also allowed, that if you take two functions, then under appropriate hypothesis, addition of the individual integrations will give you integration of the addition of the functions. Okay, great. So you have the linearity of the integration procedure that we have discussed. Great. Now with this observation at hand, you can now make this important comment that if both f and g are integrable, then f plus g is also integrable. Why? Because observe that if f and g both are integrable, then integration of mod f is finite and integration of mod g is finite. This is by the equivalent condition that we just discussed in a few minutes back. But then integration of mod of f plus g will be dominated by the addition of the integration of mod f plus mod g, because mod of f plus g is less equals to mod f plus mod g. So use that and use the additivity of the integrals, you get this inequality. But if integration of mod f is finite and the integration of mod g is finite, the addition is also finite. So therefore integration of mod f plus g is also finite, and hence f plus g becomes integrable provided f and g both are integrable. Nice. And we finish our discussion with this nice corollary that we can now talk about certain series of functions. So take non-negative Borel measurable functions, a sequence of that. Okay, a sequence of non-negative Borel measurable functions. Then consider this infinite combination, infinite summation. So this linear combination, infinite linear combination, will give you a limit function. This is an addition of non-negative quantities, so you will get a limit function. So you are considering the integration of that on the left hand side. On the right hand side, you are saying look at the individual integrations and add them up. If you are looking at these integrations of non-negative measurable functions, these quantities are non-negative, so therefore this summation is defined. This summation could be infinity, that is fine. Okay, we are saying this equality holds. So you can exchange this infinite series and the integration here. Okay, that is an important observation. So how do you prove this? Observe that the finite sum from n equal to 1 to m of the functions hn increase to the limit function, which is the complete summation, right? For this finite sum n from 1 to m, if you look at this functions hn, then these finite sum increase to the complete countable sum. But then what is happening is that for the finite sum, you can exchange the integration and the sum that is by the additivity, and apply limit in m as all these functions are increasing to this complete summation now, and by the MCT you get the required result that you can exchange the series and the integration. Great. So with these properties we are now ready to discuss computations involving expectations of random variables. That discussion we are going to have in the next lecture. We stop here.